Welcome. In this video, we'll look at functions. So, function is basically a mapping from set A to set B, or it's a mapping between the two sets A and B. So, we say that there exists a function f between the sets A and B if b is equal to f of a and b is the unique element of b assigned by function f to an element of a. So it's a mapping between elements of set a and set b. Sometimes functions are also called as transformation. So in this example here, the set a is students and set b is grades, and there's a mapping from student to grade which indicates what grade a student has scored in the examination. So, for a given examination, a student can score only one grade, and therefore, the grade is a unique element of the set B assigned to a student of set A by a mapping which we can say it's a function. Now, sometimes function is also described as subset of a Cartesian product of two sets, that is A cross B. Relations are also described as subset of Cartesian products of two sets, that is A and B. The functions are more restricted compared to relation, whereas relations are more broader in their sense. Now, to describe few terminologies about the function, if f is a mapping from set A to set B, then then A is called as domain of function f, B is called as codomain of function f. If B is equal to f of A, then B is called as image of A and A is called as pre-image of B. All the elements from the codomain set, all the elements from a codomain set collected together is called as range of set A or domain set range of domain set. So let us understand the terminologies by this example. So there are two arbitrary sets A and B, and there's a mapping as shown in the figure. Now f of A, the image of element A is Z. The image of D is again Z. The domain of f is set A. The codomain of the function f is B. The pre-image of y is element B. The range of domain A is all the elements from set B who are images of uh, elements in set A. So in this example, B has three elements x, y, and z. X is unmapped. Y and z are images of elements of set A. So y and z forms a range of the domain set. Then pre-image of z is or R is all the elements for whom z is image. So there are three pre-images A, C, and D. Now, in this example, we have ABC to be a subset of domain set and its mapping is Y and Z. Similarly, CD is a subset of domain set and its mapping is the element Z. Now, injective is a type of the function, and a function f is said to be one-to-one or injective uh, if and only if f of a equal to f of b implies that a is equal to b. Uh, to be very simple, a function is injective if every element in the codomain is image of exactly one element in the domain. Every element in the codomain is image of exactly one element in the codomain. By rule of function, an element in codomain can be image of many elements of domain set. But for an injective function, if the element in the codomain is image of exactly one element in the domain, then the function is one to one. So here in this example, there are two sets A and B, and if you look at set B, which is a codomain set, X, Y, Z, and W are images, but they are images for exactly one element, wherein V is not an image for any element. So such function is said to be one to one. The second type of function is surjective or surjection. Now, in surjective, or it is also called as a onto function, in which every element of codomain should be an image of at least one element in the domain. So every element in the codomain should be an image. Such function is called as an onto function or surjective function. A mix of injective and surjective is called as bijective. So if function is one-to-one correspondence or bijection, then it is both one-to-one and onto. That is, it is both injective and surjective. What does this mean? That every element in the codomain should be image for exactly one element in the domain. That is injective. And second, every element in the codomain should be image of at least one element in the domain. That is, every element in the codomain should be an image of an element in the domain. So mix of these two gives us a bijective function. There are two more properties of a bijective function. One is, if you look at the diagram for the onto function, in onto function, the cardinality of set B could be equal or less than set A. That is, cardinality of codomain could be equal or less than the domain set. In case of one-to-one function, the cardinality of codomain could be equal to the domain or greater than the domain. But in case of bijection, the cardinality of domain and codomain should be exactly same, so that there is both one-to-one mapping as well as there is an every element of codomain is an image of some element of set A. Now, let us look at few examples. That is, if f is a function from abcd to 1 to 3, defined by f of a equal to 3, f of b equal to 2, f of c equal to 1, and f of d equal to 3, is the function f an onto function. So in this case, we can see that there are 1 to 3 elements, 1 to 3 elements, and f is onto since all the three elements, that is all the elements from domain, sorry, from the codomain are image of an element in the domain. So therefore this function f is onto. But if we inverse the mapping, that is from 1 2 3 4 as a codomain, and that is, if we just change the codomain to 1 2 3 4, then we will find that 4 is not an image of anyone, and therefore the function is not onto. So again, for a function to be onto, every element should be an image of some element in the domain. Example 2, is the function f of x equal to x square from the set of integers to set of integers onto. Now here in this case, this function is not onto because there is no integer x with x square equal to -1. Okay, but there could be many more examples for this. Now let us talk about an inverse function. If f is a function from set A to set B, f inverse is a function from set B to set A. So if f of A is equal to B, then f inverse of B is equal to A. A inverse function between the two sets is possible if the function between A and B is a bijection. So if there is no bijective function between the sets A and B, then f inverse does not exist. So f inverse is possible, that is f inverse y is equal to x, if f of x equal to y is bijective. Okay, is bijective. So this is a typical example of what is bijective function. So first of all, when the function is bijective, the cardinality of domain and codomain is same, and and every element uh, can have inverse mapping from the codomain to domain, which through an inverse function. So for example, here let f be the function from abc to 1 to 3 such that f of a is equal to 2, f of b is equal to 3, and f of c is equal to 1. Is f invertible, and if so, what is its inverse? So first of all, we have to look for cardinality of the two sets. So abc and 1 to 3, the cardinality is same. Look for the mapping. F of a is equal to 2. 2 is image of a. Is 2 image of any other element? No. So all the elements abc have unique image in the codomain, and therefore this is 1 to 1. Moreover, how many elements are there in the codomain? 1 to 3. 3 elements are there in the codomain, and and each one is image of a distinct element, and therefore there is a inverse mapping possible such that f inverse 1 is equal to c, f inverse 3 is equal to b, f inverse 2 is equal to a. So that is how the mapping is possible. Okay. Now, how to solve a inverse function for some mathematical expression. So for example, let f be the function from set of integers to set of integers where f of x is equal to x plus 1. Okay, y is equal to f of x. Now, is this function invertible? The function is invertible only if there is a bijection. Now, yes, the bijection is quite possible because the integer set domain and codomain run from minus infinity to plus infinity, and therefore y is equal to x plus 1 or f of x is equal to x plus 1 will be a bijective function. Now, how to solve this? Represent the function as y is equal to f of x is equal to x plus 1. Replace x with y with x, so you get an equation x is equal to y plus 1. Solve this equation to get y is equal to something. So if I solve this equation, we get y is equal to x minus 1, which is the inverse function. Y is equal to x minus 1 is an inverse function. So let f be a function from set of real numbers to set of real numbers such that f of x equal to x square. Is f invertible, and if so, what is the inverse? So first of all, this function is not invertible because it's not one to one, because every real number is not a perfect square. Now let us move on to composition of function. Composition of function talks about combining two functions, and it is generally denoted by f of g. So f of g is a composite function. So f of g of x is equal to f of g of x. So consider three sets a, b, and c, and g is a function between the two sets a, b. F is a function between the two sets b, c. Then f of g is a composite function from set a to set c. Okay, f of g is a composite function from set a to set c as shown in this figure. Here you can look at this. There are three sets A, B, and C. G is a function from set A to B. F is a mapping from set B to set C. So B is a codomain for function G, and as against it's a domain for function F. Now the composite function f of g, as A is mapped to y and y is mapped to j, in a composite function A is mapped to j. Okay, similarly, B is mapped to W, W is mapped to H, so B is also mapped to H. Similarly, D is mapped to W, W is mapped to H, so D is mapped to H in the composite function. C is mapped to X, X to I, and therefore C is mapped to I. So this is the composite function f of g from set A to set C. So how to solve this composite function for the numerical function? So f of x is equal to x square and g of x is equal to 2x plus 1. So f of g of x is equal to g of x is 2x plus 1. So this becomes f of 2x plus 1. Now f of x is x square. So the final result becomes 2x plus 1 square. And similarly, g of f of x is equal to x square. G of x is 2x plus 1. So this becomes 2x square plus 1. Again, f of g of x and g of f of x is not same. So in other words, f of g and g of f are not same operations. They are not equal operations. Okay, let us take this an example. Let j be a function from set abc to itself with g of a equal to b, g of b equal to c, and g of c equal to a. Let f be the function from set abc to set 1 to 3 such that f of a is equal to 3, b is equal to 2, and c is equal to 1. What is the composition of f and g, and what is the composition of g and f? So what we understand from this, the composition of f of g of a is f of g of a. So f of b is f of g of a. So g of a is equal to b, and so f of b is equal to 2. So f of g of a is equal to 2. So a is mapped with 2. F of g of b is equal to f of g of b. G of b from the problem is equal to c, and f of c from the problem is equal to 1. So f of g of b is equal to 1. Uh, now, to understand, g of f is not defined because the range of f is not a subset of domain of g. So the range of the f is not subset of domain of g, and therefore we cannot define g of f as a composition. You can go into the details of this by drawing a diagram too. Let's consider one more example. that if f and g be the functions from set of integers to set of integers, that is from z to z, f of x is equal to x plus 3, g of x is equal to 3x plus 2, find the composite functions. So we get f of g of x as f of g of x is equal to f of g of x. G of x is 3x plus 2. So f of 3x plus 2 is equal to 2 into 3x plus 2 plus 3, which is equal to 6x plus 7. And g of f of x is equal to g of 2x plus 3, equal to 3 into 2x plus 3 plus 2, which is 6x plus 11. We can represent functions by using graphs. So for example, uh, a line of a equation of a straight line, that is mx plus c or 2n plus 1 in this case, can be represented as a function on a graph. So dotted dark circles indicate that that's a line. Similarly, f of x equal to x square will give us a u shape or u shaped curve from set of integers to set of integers. Then floor and ceiling are some standard functions where floor indicates that if there is a real number 3.5, it will give equal to 3 as an integer. Ceiling indicates if 3.5 is a real number, it will be rounded to 4. This works exactly reverse. For minus 1.5, ceiling is minus 1 and floor is minus 2.